Next section we're covering is 14.3. I did not making a video for limits and continuity. That's not going to be on the exam. So 14.3, partial derivatives. This is really where things start to pick up the pace a little bit. Certainly here in differentiability and tangent planes before completely being welcome to Calc 3 and 14.5. So partial derivatives, when you have a function of more than one variable, such as f of xy equals, let's say, x squared plus xy cubed, when you take a derivative, you now have options. You have two variables. So if you treat x as the variable and pretend y as a constant, that's exactly what an x partial derivative is, you treat the x's as your variables, you differentiate as normal, and you pretend that everything else is a constant. For the y partial derivative, you play the same game, but in this time we're treating y as the variable and pretending all other variables, or all other symbols at least, are constants for the time being. So this would end up being just 3xy squared, because this x squared is considered a constant in the eyes of y. Clairaut's theorem, right here, says that if you differentiate with respect to x first, then with respect to y, you will get the same thing as if you first differentiate with respect to y, then with respect to x. So the order of differentiation here doesn't matter, and this extends to higher order derivatives. So if you have a function of three variables, you could say fxxyz is the same thing as fzyxx. Any reordering, any permutation will still result in the same thing. In 14.3, we also did a little bit more of a conceptual understanding of the partial derivatives. As far as the final goes, the geometric interpretation of the partial derivatives as the rate of change of the curve obtained by tracing a surface z equals f of xy with yada yada yada, that you really don't go into that much depth on the final. Really, we'll use partial derivatives in the gradient and in calculating these things like that. Okay.